I'm going to go through a brief run through of this week's lab. The code is on Canvas in a PDF. The following code will run in two ways. If you have these packages already installed, it's going to default and just load in the package. If you do not have it installed, this statement's going to check to see if it's already installed. And if it's not, it'll install it first. Then it'll load it for you. So I'm going to run that. And I have everything installed. If you have any messages that say you need to install something else, please do so. Now, for me, when you first get the document, it'll be blank. You're going to need to use CSV data in the reader package. So make sure you type in library reader, run that. And then for read_CSV, you are going to have a very distinct data set. And this has been a common misconception in the past couple of weeks where folks are getting docked points. Please make sure that you are uploading your unique data set on Canvas. So I'm going to go through how I would approach filling in this path file name. I like to go to import data set, go to reader. I will browse, find my file. And then what I like to do is I will actually take this code preview, but notice my first line here is actually my data. So I need to change something. You know, to go to this option where it says first row as names. Well, we don't have any names in our data set. So I don't want that option. So I'm going to click it off and the code's going to change a little bit. It's going to say call_names equals false, meaning it's going to give you a bunch of names that are default X1 through X10. This is what it should look like. And don't worry about the names right now. We'll get back to that. So I'm going to take this code, copy it. I'm going to cancel out of this and I am going to replace it here. So now I have a data frame called df using the read_CSV function. Now this will not work for you because you need to actually put your path. For me, it's in my downloads. So I'm going to go shift tilde, which is the key next to the one, /downloads /, and that's going to be only to my computer. Yours may be different. You may put it in like 3 subfolders. You need to find out where that path is. And when I run this, it loads. I check my environment. I'm good to go. It looks exactly how it did in the preview. Now notice this next one right here, view MTMM dataset. That's not going to work because I don't have that. So if I run it, I'm going to get an error because it's not found because it's not in my environment because I called it df. And that's how you view it. I also want to note that if you are doing this in an R Markdown document, your R Markdown file will crash because it does not like this function view. So if you are going to do this in R Markdown, comment that out. Don't worry about this. These are different data set styles, which are different formats that you may use for this type of analysis. You're going to recode all the NAs. So in other words, if any of the values from df equal -999, we're going to make it missing. So when I do that, I run that and I can view it and it looks like we're good to go. Call names. This is, remember I was telling you earlier, we have X1 through X10 right here. This is going to replace those with respective variable names that we need. The first one being ID and the last one being extraversion teach. But that is do anything other than store these column names into our data set. You only want to work with the data that you need for the analysis, meaning you're not going to include the ID number because it'll actually read that as a variable. You don't want to predict someone's ID with any of these other variables. So to prep for analysis, we're going to run this code. We're going to take the data frame, df. Remember, it's row by column. So what it's saying is keep all the rows, that space there. -1 means remove the first column. And then store this entire thing in a new data set called lab6 no ID. And when I run that, boom, now I have 9 variables. I can check that out again. Now the ID column is different. Notice it's different. There's an ID column in the df and lab6 no ID, no ID. And now I could start running my models. So you'll need to do this on your own. These models are already set up for you though. You just need to make sure the code is typed correctly. Remember, 1 apostrophe to start, 1 apostrophe to end when you're building these models. You need equals tilde to tell the Lavon package that this is going to be a factor variable. So these are factors, child, parents, and teacher. And these are our indicator variables. So I'll run the first one, it runs. That's our methods model. We have a traits model, then we're gonna analyze them. Warnings are okay, don't worry. I'm gonna run the next one, and then I'm gonna inspect, and we get a matrix. You will need to research on your own what this means. Then you're gonna summarize each of them. When you summarize, you're gonna be able to get your model fit statistics, and you're going to need that for the assignment. Here's your chi-square values right here. Here's comparing to the baseline model, meaning the worst case scenario. Here's your CFI, TLI. These are bad, by the way. Note that for the exam. Here's the RMSEA value. Not great. Also not great. And then you get your standardized estimates right here and under standardized estimates on the left column. And here's the respective P values telling you if these are significant predictors. Now, when I ran this, this was for the methods model. So from here, it's not looking great in terms of the fit for the methods model. Let's look at the traits model. Definitely a lot better, not great. So you want to make sure that the model looks well. So it improved, but it's not great. The CFI is like acceptable. SRMR is good. RMSEA kind of not great. Significant predictors. Here's your unstandardized and your standardized estimates. Now, this code right here is going to give you a diagram of what it looks like. I'll get that on the side. I'll expand this a little bit. So notice it's a correlated model with 3 factors. And here you get your loadings. Notice that the loadings are currently, these are all standardized loadings. We'll run that again. That'll be for the traits model. Again, standardized loadings. We're going to use a new model, the correlated traits, correlated methods model. This is already set up for you. You'll run that, and you'll run LeBon again, and then you get a summary. And again, you're going to need to decipher what these estimates mean. Low RMSEA is good. These TLI, CFI values are good. This is good for chi-square. Okay, now I'm gonna look at the pathways for this new diagram. And notice we added more factors and that improved the model fit. Now we're gonna look at the no traits and correlated methods. So let's check it out. This first one tells you, is there a difference between the two models? You're going to need to decipher that. You'll get fit measures for each. Tell me which one's a better fit measure using CFI. For the step 3 model, we're going to improve a little bit our fit. Again, warnings are not terrible. You get a summary. Oof, not great. You'll need to tell me why. Another path with the standardized loadings. So you'll have to tell me what changed from the previous model that made that have a bad fit. And then these next 3 lines of codes need to be run, but you need to make sure that it runs for you and comment out what doesn't to make it work. Okay, there's significance. Tell me what that means. When you're looking at the different fit measures, you could see which one's a better fit using the CFI. In this last step, we're going to set the covariances between the methods to 0. In doing that, we have really good model fit statistics. You'll have to tell me why. Here's another sum paths. You can see the new diagram. You can expand this to make it larger so you can see the numbers better. You can also export this and it'll be different. There's many ways to actually make these values smaller. Don't worry about that too much because you're going to be focused on the output anyway. So now you're going to compare the models from step 1 to step 4. No significance there. So if you find that they're equal, that means you don't want them to be significant. So here, if you look at the CFIs, they're both very high. Then you're going to look at all the parameter estimates from all your models. This is just a different way to look at what you were already looking at above. What's nice about this is it gives you the path that you originally created, and it gives you p-values, your confidence intervals, and your standardized coefficients. And then your unstandardized are here. Now, to be successful on this lab, let me pull something up. So remember, you need your unique data set number. For question 1, to answer this, you're going to need to refer to whether the optimization algorithm arrived at the final solution or not. To do this, you're going to need to look at the summary of the output for each of your models. So the methods.fit, traits.fit, step 1.fit, step 3.fit, and step 4.fit to check if it converged. For question 2, evaluate the fit of your models. Does the model fit well? Well, you're going to use the fit statistics that I just talked about. So for example, you would want to look at chi-square and its p-value from the output, the CFI values, the TLI values, the RMSEA, the SRMR. Remember your cutoffs for number 3. To examine the reliability of your observed indicators, you want to look at the standardized parameter estimates. And that was the last part of code I just showed you. Those last couple lines for the parameter estimates code. Look for each of those models, make sure standardized equals true is set. And what you're going to do is you're going to take the least reliable observed indicator, find the smallest standardized factor loading, and then you want to also find the most reliable observed indicator. So find the largest standardized factor loading using the same command. Interpret the reliability based on those values. For question 4, to evaluate the amount of trait and method variance in the observed variables, you can interpret the trait and method variance by looking at the standardized factor loadings and the uniqueness, so the error variances of the observed variables. And you would expect these in the various models built. So the methods.model, traits.model, using the parameter estimates function at the very end. To compare these trait variances to the trait factor correlations, which is question 5, you want to look at the point estimates for the correlations between the traits and the confidence intervals for those estimates. So you can use the functions like LABay inspect, which is in the beginning of the code. Now for question 6, it's a little different. Here's a guide to kind of see what to look for in the outputs. For convergence and discrimination of traits, you want to compare the models to see if the traits are different from one another. And this can be found in the ANOVA step1.fit, step3.fit, and other model comparisons as well. If the model's constrained trait correlations are significantly worse, then there may be a lack of discriminant validity among traits. You want to look at the correlations between traits from the LOB inspect function. So if these are low, it suggests good discriminant validity. For model fit, you want to assess good fit statistics using summary and those fit measures. So check again, chi-square, CFI, RMSEA, SRMR. For convergent validity though, you want to look at the standardized factor loadings in the parameter estimates function. High loadings on expected traits suggest convergent validity. Compare trait loadings with method loadings to see if trait factor loadings are higher and whether or not that supports convergent validity. You want to analyze the ANOVA results between the models with and without the traits. So for example, when we had the function ANOVA, open parentheses, step1.fit, methods.fit. That's a hint. So you want to look at that to see if adding traits improves the model fit, which would further support convergent validity. For reliability of indicators, you want to analyze the least and most reliable observed indicators, so from question 3, to see if they're consistent and strong loadings on the intended factors. So combining these findings to make a judgment about construct validity, you would also need strong construct validity, which would be supported if there is evidence of good fit. Also, if there's strong and consistent factor loadings, evidence of convergent and discriminant validity among traits, and no contradictions across the different models and steps of the analysis.